infinity is an abstract concept describing something without any limit and is relevant in a number of fields, predominantly mathematics and physics. The English word infinity derives from Latin infinitas, meaning being without finish, and which can be translated as unboundedness, itself calqued from the Greek word apeiros, meaning endless. In mathematics, infinity is often treated as if it were a number, but it is not the same sort of number as the real numbers. In number systems incorporating infinitesimals, the reciprocal of an infinitesimal is an infinite number, that is, a number greater than any real number. Georg Cantor formalized many ideas related to infinity and infinite sets during the later 19th and early 20th centuries. In the theory he developed, there are infinite sets of different sizes. For example, the set of integers is countably infinite, while the infinite set of real numbers is uncountable. History. Ancient cultures had various ideas about the nature of infinity. The ancient Indians and Greeks did not define infinity in precise formalism as does modern mathematics, and instead approached infinity as a philosophical concept. Early Greek. The earliest recorded idea of infinity comes from Anaximander, a pre-Socratic Greek philosopher who lived in Miletus. He used the word apeiron, which means infinite or limitless. However, the earliest attestable accounts of mathematical infinity come from Zeno of Elea, a pre-Socratic Greek philosopher of southern Italy and member of the Eleatic school founded by Parmenides. Aristotle called him the inventor of the dialectic. He is best known for his paradoxes, described by Bertrand Russell as immeasurably subtle and profound. In accordance with the traditional view of Aristotle, the Hellenistic Greeks generally preferred to distinguish the potential infinity from the actual infinity. For example, instead of saying that there are an infinity of primes, Euclid prefers instead to say that there are more prime numbers than contained in any given collection of prime numbers. However, recent readings of the Archimedes palimpsest have hinted that Archimedes at least had an intuition about actual infinite quantities. Early Indian, the Indian mathematical text Pranapti classifies all numbers into three sets: innumerable, innumerable, and infinite. Each of these was further subdivided into three orders: innumerable lowest, intermediate, and highest, innumerable, nearly innumerable, truly innumerable, and innumerably innumerable, infinite, nearly infinite, truly infinite, infinitely infinite. In this work, two basic types of infinite numbers are distinguished. On both physical and ontological grounds, a distinction was made between Asia to the first Florin Iota and Ananta, between rigidly bounded and loosely bounded infinities. Mathematics, infinity symbol. The infinity symbol is a mathematical symbol representing the concept of infinity. The symbol is encoded in Unicode at U+221 EA infinity and in LaTeX is \infty. It was introduced in 1655 by John Wallis, and, since its introduction, has also been used outside mathematics in modern mysticism and literary symbology. Calculus. Leibniz, one of the co-inventors of infinitesimal calculus, speculated widely about infinite numbers and their use in mathematics. To Leibniz, both infinitesimals and infinite quantities were ideal entities, not of the same nature as appreciable quantities, but enjoying the same properties. Real analysis. In real analysis, the symbol, called infinity, is used to denote an unbounded limit. Means that x grows without bound, and means the value of x is decreasing without bound. If f, t, a permel 0 yen for every t, then, means that f, t, does not bound a finite area from 2, means that the area under f, t, is infinite. Means that the total area under f, t, is finite, and equals. Infinity is also used to describe infinite series, means that the sum of the infinite series converges to some real value. Means that the sum of the infinite series diverges in the specific sense that the partial sums grew without bound. Infinity can be used not only to define a limit but as a value in the extended real number system. Points labeled and can be added to the topological space of the real numbers, producing the two-point compactification of the real numbers. Adding algebraic properties to this gives us the extended real numbers. We can also treat and as the same, leading to the one-point compactification of the real numbers, which is the real projective line. Projective geometry also refers to a line at infinity in plane geometry, a plane at infinity in three-dimensional space, and so forth for higher dimensions. Complex analysis. In complex analysis the symbol, called infinity, denotes an unsigned infinite limit. Means that the magnitude d of x grows beyond any assigned value. A point labeled can be added to the complex plane as a topological space giving the one-point compactification of the complex plane. When this is done, the resulting space is a one-dimensional complex manifold, or Riemann surface, called the extended complex plane or the Riemann sphere. Arithmetic operations similar to those given above for the extended real numbers can also be defined, though there is no distinction in the signs. On the other hand, this kind of infinity enables division by zero, namely for any non-zero complex number as z. In this context it is often useful to consider meromorphic functions as maps into the Riemann sphere taking the value of at the poles. The domain of a complex-valued function may be extended to include the point at infinity as well. One important example of such functions is the group of Marr paragraph bias transformations. Non-standard analysis. The original formulation of infinitesimal calculus by Isaac Newton and Gottfried Leibniz used infinitesimal quantities. In the 20th century, it was shown that this treatment could be put on a rigorous footing through various logical systems, including smooth infinitesimal analysis and non-standard analysis. In the latter, infinitesimals are invertible, and their inverses are infinite numbers. The infinities in this sense are part of a hyperreal field. There is no equivalence between them as with the Cantorian transfinites. For example, if for h is an infinite number, then h plus a high equals a2 hours and h plus a1 are distinct infinite numbers. This approach to non-standard calculus is fully developed in Kiesler. Set theory. A different form of infinity are the ordinal and cardinal infinities of set theory. Georg Cantor developed a system of transfinite numbers, in which the first transfinite cardinal is Aleph null, the cardinality of the set of natural numbers. This modern mathematical conception of the quantitative infinite developed in the late 19th century from work by Cantor, Gottlob Frege, Richard Dedekind and others, using the idea of collections, or sets. Dedekind's approach was essentially to adopt the idea of one-to-one correspondence as a standard for comparing the size of sets, and to reject the view of Galileo that the whole cannot be the same size as the part. An infinite set can simply be defined as one having the same size as at least one of its proper parts. This notion of infinity is called Dedekind Infinite. The diagram gives an example, viewing lines as infinite sets of points. The left half of the lower blue line can be mapped in a one-to-one manner to the higher blue line, and, in turn, to the whole lower blue line. Therefore the whole lower blue line and its left half have the same cardinality, that is size. Cantor defined two kinds of infinite numbers, ordinal numbers and cardinal numbers. Ordinal numbers may be identified with well-ordered sets, or counting carried on to any stopping point, including points after an infinite number have already been counted. Generalizing finite and the ordinary infinite sequences which are maps from the positive integers leads to mappings from ordinal numbers, and transfinite sequences. Cardinal numbers define the size of sets, meaning how many members they contain, and can be standardized by choosing the first ordinal number of a certain size to represent the cardinal number of that size. The smallest ordinal infinity is that of the positive integers, and any set which has the cardinality of the integers is countably infinite. If a set is too large to be put in one-to-one correspondence with the positive integers, it is called uncountable. Cantor's views prevailed and modern mathematics accepts actual infinity. Certain extended number systems, such as the hyperreal numbers, incorporate the ordinary numbers and infinite numbers of different sizes. Cardinality of the continuum. One of Cantor's most important results was that the cardinality of the continuum is greater than that of the natural numbers. That is, there are more real numbers than natural numbers and namely, Cantor showed that. The continuum hypothesis states that there is no cardinal number between the cardinality of the reals and the cardinality of the natural numbers, that is, However, this hypothesis can neither be proved nor disproved within the widely accepted Zermelo-Fractal set theory, even assuming the axiom of choice. Cardinal arithmetic can be used to show not only that the number of points in a real number line is equal to the number of points in any segment of that line, but that this is equal to the number of points on a plane and, indeed, in any finite-dimensional space. The first of these results is apparent by considering, for instance, the tangent function, which provides a one-to-one correspondence between the interval and r. The second result was proved by Cantor in 1878, but only became intuitively apparent in 1890, when Giuseppe Peano introduced the space-filling curves, curved lines that twist and turn enough to fill the whole of any square, or cube, or hypercube, or finite-dimensional space. These curves can be used to define a one-to-one correspondence between the points in the side of a square and those in the square. Geometry and topology. Infinite-dimensional spaces are widely used in geometry and topology, particularly as classifying spaces, notably Eilenberg-MacLane spaces. Common examples are the infinite-dimensional complex projective space K, Z, 2, and the infinite-dimensional real projective space K, Z/2Z, 1. Fractals. The structure of a fractal object is reiterated in its magnifications. Fractals can be magnified indefinitely without losing their structure and becoming smooth. They have infinite perimeter some with infinite, and others with finite surface areas. One such fractal curve with an infinite perimeter and finite surface area is the Koch snowflake. Mathematics without infinity. Leopold Kronecker was skeptical of the notion of infinity and how his fellow mathematicians were using it in the 1870s and 1880s. This skepticism was developed in the philosophy of mathematics called finitism, an extreme form of the philosophical and mathematical schools of constructivism and intuitionism. Physics. In physics, approximations of real numbers are used for continuous measurements and natural numbers are used for discrete measurements. It is therefore assumed by physicists that no measurable quantity could have an infinite value, for instance by taking an infinite value in an extended real number system, or by requiring the counting of an infinite number of events. It is, for example, presumed impossible for any type of body to have infinite mass or infinite energy. Concepts of infinite things such as an infinite plane wave exist, but there are no experimental means to generate them. Theoretical applications of physical infinity. The practice of refusing infinite values for measurable quantities does not come from a priori or ideological motivations, but rather from more methodological and pragmatic motivations. One of the needs of any physical and scientific theory is to give usable formulas that correspond to or at least approximate reality. As an example, if any object of infinite gravitational mass were to exist, any usage of the formula to calculate the gravitational force would lead to an infinite result, which would be of no benefit since the result would be always the same regardless of the position and the mass of the other object. The formula would be useful neither to compute the force between two objects of finite mass nor to compute their motions. If an infinite mass object were to exist, any object of finite mass would be attracted with infinite force by the infinite mass object, which is not what we can observe in reality. Sometimes infinite result of a physical quantity may mean that the theory being used to compute the result may be approaching the point where it fails. This may help to indicate the limitations of a theory. This point of view does not mean that infinity cannot be used in physics. For convenience's sake, calculations, equations, theories and approximations often use infinite series, unbounded functions, etc., and may involve infinite quantities. Physicists however require that the end result be physically meaningful. In quantum field theory infinities arise which need to be interpreted in such a way as to lead to a physically meaningful result, a process called renormalization. However, there are some theoretical circumstances where the end result is infinity. One example is the singularity in the description of black holes. Some solutions of the equations of the general theory of relativity allow for finite mass distributions of zero size, and thus infinite density. This is an example of what is called a mathematical singularity, or a point where a physical theory breaks down. This does not necessarily mean that physical infinities exist. It may mean simply that the theory is incapable of describing the situation properly. Two other examples occur in inverse square force laws of the gravitational force equation of Newtonian gravity and Coulomb's law of electrostatics. R to R equals 0. These equations evaluate to infinities. Cosmology. In 1584, the Italian philosopher and astronomer Giordano Bruno proposed an unbounded universe in On the infinite universe and worlds, innumerable suns exist. Innumerable Earths revolve around these suns in a manner similar to the way the 7 planets revolve around our Sun. Living beings inhabit these worlds. Cosmologists have long sought to discover whether infinity exists in our physical universe. Are there an infinite number of stars? Does the universe have infinite volume? Does space go on forever? This is an open question of cosmology. Note that the question of being infinite is logically separate from the question of having boundaries. The two-dimensional surface of the Earth, for example, is finite, yet has no edge. By traveling in a straight line one will eventually return to the exact spot one started from. The universe, at least in principle, might have a similar topology. If so, one might eventually return to one's starting point after traveling in a straight line through the universe for long enough. If, on the other hand, the universe were not curved like a sphere but had a flat topology, it could be both unbounded and infinite. The curvature of the universe can be measured through multiple moments in the spectrum of the cosmic background radiation. As to date, analysis of the radiation patterns recorded by the WMAP spacecraft hints that the universe has a flat topology. This would be consistent with an infinite physical universe. However, the universe would also be finite, even if its curvature is flat. An easy way to understand this is to consider two-dimensional examples, such as video games where items that leave one edge of the screen reappear on the other. The topology of such games is toroidal and the geometry is flat. Many possible bounded, flat possibilities also exist for three-dimensional space. The concept of infinity also extends to the multiverse hypothesis, which, when explained by astrophysicists such as Michio Kaku, posits that there are an infinite number and variety of universes. Logic. In logic, an infinite regress argument is a distinctively philosophical kind of argument purporting to show that a thesis is defective because it generates an infinite series when either no such series exists or were it to exist, the thesis would lack the role that it is supposed to play. Computing, the Yee floating point standard specifies the positive and negative infinity values. These are defined as the result of arithmetic overflow, division by zero, and other exceptional operations. Some programming languages, such as Java and J, allow the programmer an explicit access to the positive and negative infinity values as language constants. These can be used as greatest and least elements, as they compare greater than or less than all other values. They are useful as sentinel values in algorithms involving sorting, searching, or windowing. In languages that do not have greatest and least elements, but do allow overloading of relational operators, it is possible for a programmer to create the greatest and least elements. In languages that do not provide explicit access to such values from the initial state of the program, but do implement the floating point data type, the infinity values might still be accessible and usable as the result of certain operations. Arts and cognitive sciences, perspective artwork utilizes the concept of imaginary vanishing points, or points at infinity, located at an infinite distance from the observer. This allows artists to create paintings that realistically render space, distances, and forms. Artist M.C. Escher is specifically known for employing the concept of infinity in his work in this and other ways. Cognitive scientist George Lakoff considers the concept of infinity in mathematics and the sciences as a metaphor. This perspective is based on the basic metaphor of infinitia, BMI, defined as the ever-increasing sequence less than 1, 2, 3. The symbol is often used romantically to represent eternal love. Several types of jewelry are fashioned into the infinity shape for this purpose. See also, 0.999. Aleph number, infinite monkey theorem, infinite set, paradoxes of infinity, Surreal Number, Notes. References, J. Magnani, Michael C., Elementary Topology, Dover, ISBN A0-486-66522-4, Kiesler, H. Jerome, Elementary Calculus, An Approach Using Infinitesimals, Maddox, Randall B., Mathematical Thinking and Writing, A Transition to Abstract Mathematics, Academic Press, ISBN A0-12-464976-9, Swokowski, L.W., Calculus with Analytic Geometry, Prindle, Weber and Schmidt, ISBN A0-87150-341-7, Taylor, Angus E., Advanced Calculus, Blaisdell Publishing. Campagna, David Foster Wallace. Everything and More, A Compact History of Infinity. Norton, W. W. and Company, Incorporated. ISBN A0-393-32629-2. Further reading, Amir D. Achal. The Mystery of the Aleph, Mathematics, the Kabbalah, and the Search for Infinity. New York, Pocket Books. ISBN A0-7434-2299-6. D. P. Agrawal. Ancient Jaina Mathematics, An Introduction, Infinity Foundation. Bell, J. L. Continuity and Infinitesimals. Stanford Encyclopedia of Philosophy. Revised 2009. L. C. Jain. Exact Sciences from Jaina Sources. L. C. Jain. Set Theory in the Jaina School of Mathematics, Indian Journal of History of Science. George G. Joseph. The Crest of the Peacock, Non-European Roots of Mathematics. Penguin Books. ISBN A0-14-027778-1. Eli Moon. To Infinity and Beyond. Princeton University Press. ISBN A0-691-02511-8. Rudy Rucker. Infinity and the Mind, The Science and Philosophy of the Infinite. Princeton University Press. ISBN A0-691-00172-3. Navoti Singh. Jaina Theory of Actual Infinity and Transfinite Numbers. Journal of Asiatic Society 30. External links, The Infinite Entry in the Internet Encyclopedia of Philosophy, Infinity on In Our Time at the BBC. A Crash Course in the Mathematics of Infinite Sets, by Peter Subber. From the St. John's Review, XLIV, 21 €59. The standalone appendix to Infinite Reflections, below. A concise introduction to Cantor's Mathematics of Infinite Sets. Infinite Reflections, by Peter Subber. How Cantor's Mathematics of the Infinite solves a handful of ancient philosophical problems of the infinite. From the St. John's Review, XLIV, 21 €59. Grime, James. Infinity is Bigger Than You Think. Numberphil. Brady Heron. Infinity, Principia Cybernetica, Hotel Infinity, John J. O'Connor and Edmund F. Robertson. Georg Ferdinand Ludwig Philipp Cantor, Maxiter History of Mathematics Archive. John J. O'Connor and Edmund F. Robertson. Jaina Mathematics, Maxiter History of Mathematics Archive. Ian Pearce. Jainism, Maxiter History of Mathematics Archive. Source page on Medieval and Modern Writing on Infinity, The Mystery of the Aleph, Mathematics, the Kabbalah, and the Search for Infinity, Dictionary of the Infinite.